Assalamu alaikum friends. I'm Taqdees Siddiqui with Computer Graphics for Bachelor's in Computer Science course being offered by Virtual University, Government of Pakistan. Today is our 38th lecture. We have started our discussion about curves and we are going to take it a little further today. We will be talking about Bezier curves today. So let's begin our discussion. Bezier curves is an important part of almost every computer graphics illustration program and computer-aided design system in use today. We'll find it to be an integral part of all such applications. Primarily, it originated from a computer-aided design requirement, as we will get to know shortly. It is used in many ways, from designing the curves and surfaces of automobiles to defining the shape of letters in type fonts. Because it is numerically the most stable of all the polynomial-based curves used in these applications, the Bezier curve is the ideal standard for representing the more complex piecewise polynomial curves. When we talk about complex curves, we have such requirements which might not be sufficed using a single polynomial, and that is when the concept of piecewise polynomials walks in. Piecewise polynomials का concept ये है कि जब हमारे पास ऐसा कोई कॉम्प्लेक्स कर्व आ जाए जिसके लिए कोई एक पॉलिनोमियल जो है वो उसको जनरेट करने से कासिर हो, तो फिर हम इस तरह से करते हैं कि उसके मुख्तलिफ हिस्से कर लेते हैं. हर एक हिस्से को या हर एक पीस को हम एक अलग पॉलिनोमियल के जरिए से रिप्रेजेंट कर लेते हैं और इस तरीके से इन तमाम पॉलिनोमियल्स को फिर इकट्ठा करके फाइनली एक कर्व, कॉन्टिन्यूस कर्व वो बनाया जा सकता है. नेचुरली उसकी कुछ रिक्वायरमेंट्स हैं, कुछ उसकी शराइत हैं, दे हैव टू बी मेट, बट basic concept is that of breaking a curve into pieces and then framing polynomials for each of those pieces, and that forms the piecewise polynomial. In the early 1960s, Peter Bezier began looking for a better way to define curves and surfaces, one that would be useful to a designer or design engineer. Primarily, he was working on the design of Renault's automobiles and Citroën car, and that led him to what we today know as the Bezier curve. Very interesting topic that we are going to talk about today. We'll try to get to know the basic theory lying behind these curves and then how to make those curves. There are multiple different algorithms. The most popular of those is given by de Castro's. De Castro's algorithm can actually be implemented making use of tools like C or C++ that you already know. We will be talking about the basic theory lying behind the Bezier curves today. A geometric construction of Bezier curves is what we start our discussion with. We can draw a Bezier curve using a simple recursive geometric construction. Let's begin by constructing a second degree curve. For that, we select 3 points, A, B, and C, so that line AB is a tangent to the curve at point A, and BC is tangent to the curve at point C. The curve begins at point A and ends at point C. So these are the two end points of the curve, and we have got two tangents that are tangents at points A and C, and they are meeting at point B. Take a look at this illustration. For the moment, only concentrate on A, B, and C. So the segment AB is tangent at point A of the curve, and BC is tangent at point C of the curve. For the moment, don't worry about the D, E, and F. So that's what we are starting our discussion with. Two tangents at the two end points of the curve. For any ratio UI, we construct points D and E such that AD over AB is equal to BE over BC, which equals UI. Let's mark it as equation number 1. Basic idea is that we make use of this U, the good old U that we have been talking about, as an independent variable, and we will give it some values arbitrarily. With varying values for UI, we will be able to come up with multiple points on the boundary of the curve. The basic idea would be that, say, for instance, we start by a small value for UI in between 0 and 1. We take, say, 0.1 as the starting value. then that would serve as the ratio between the two segments that we are going to come up with for the line segment AB and for BC. That UI would be same, would be kept same for one iteration of finding these points. So we'll find a point on segment AB, and similarly with the same ratio we'll find another point on segment BC. Successively, the points that we have found would serve as the new endpoints for our process to be repeated, and the same process of finding the point on the segment would be repeated for this new segment now. We have worked with AB and BC. Now if we have introduced the new segment as, say, DE, we are going to use the same UI as the ratio to find a point on that line segment. And this point would be the final point, in this case when we have started off with 3 points, A, B and C only, and that would be a point on the surface, on the boundary of the curve. That's the basic philosophy. We are going to repeat this process step by step now. So we mark this equation as the first equation, equation number 1, where AD over AB is equal to BE over BC is equal to UI. On DE, we construct point F so that DF over DE is equal to UI. Point F is on the curve. Why? Because we started off with 3 points only, A, B, C. We had 2 segments, AB and BC, to play with. We used some arbitrary value for UI and found 2 points on these 2 segments. The line joining these 2 new points was our target next, and we found another point that was using the same ratio UI on this segment, new segment, and that is all that we have. 2 segments थे initially हमारे पास, उन 2 से 1 बना, उस 1 पर जब 1 point मिलेगा तो there is no further process repeatable. UI ratio के तौर पे इस्तेमाल हुआ for the segment AB as well as for BC, and similarly same ratio is used on the segment DE, और उसके ऊपर जो हमें point मिलता है, that point is the point F over here, which lies on the boundary of the curve. Repeating this process for other values of UI, we produce a series of points on a Bezier curve. As I said earlier, UI की value arbitrarily हम रखते हैं. So if we start with point 1, next iteration में उसकी value point 2 कर देते हैं, point 3, point 4, so on up to 1 चले जाते हैं. So ultimately we'll be able to find 10 points on the curve in this particular scenario. अब वो 10 points अगर हमें मिल जाते हैं और उन 10 points को हम मिला लेते हैं, आपस में जोड़ लेते हैं, we'll be able to come up with a curve. इससे पहले तक हम जो बेसिक आइडिया इस्तेमाल करते आ रहे हैं कर्व्स की डेफिनेशन के लिए, कर्व को बनाने के लिए, वो है इंटरपोलेशन का, जिसके अंदर हम पॉइंट्स फाइंड करते हैं जिनको हम इंटरपोलेट करके वो कर्व डिफाइन कर सकें. लेकिन अब जो आइडिया बेजियर कर्व हमें दे रहा है वो इंटरपोलेशन का नहीं है. दैट इज दैट ऑफ अप्रोक्सीमेशन. सो व्हाट वी आर डूइंग इज दैट वी आर अप्रोक्सीमेटिंग द कर्व. वी आर मेकिंग यूज ऑफ 2 एंड पॉइंट्स. वो तो इंटरपोलेट होते ही हैं, पहला पॉइंट और आखिरी पॉइंट जो है कर्व का, उन दोनों को तो इंटरपोलेट होना, जहां से कर्व शुरू होगा और जहां खत्म होगा, दोज पॉइंट्स वुड बी इंटरपोलेटेड. But all other points that we'll have would serve as control points, and they would not be interpolated. They would be controlling the shape of the curve by the method of approximation. We'll get to appreciate that point as well pretty shortly. Take a look at the same figure again. This time do consider the segment DE as well. So whatever arbitrary value was used for UI, that gave us point D on segment AB and gave us the point E on BC. Now these 2 points D and E, they are joined by the segment DE. Using the very same UI, we repeated the same process of finding a point on this segment, and that point that we found was F, and you can see it is on the boundary of the curve. Now this process, if repeated with different various values of UI, that would give us multiple points on the curve. And all those points would help us define the curve ultimately. But you can see here that primarily we started off with A, B and C, out of which only A and C, the 2 endpoints, they have been interpolated. But the third point, B, that stays away from the boundary of the curve. It is not being interpolated. It is only being used for approximating the shape of the curve. So depending upon where B lies, the curve is going to have a different shape. Note that we must be consistent in the order in which we subdivide AB and BC. For example, here first AB is divided into AD and DB, and then BC into BE and EC, and finally DE into DF and FE. So if we are making use of UI, we start off with some specific value which might serve as a point to be found nearer our first endpoint. From, if we are talking about the segment AB, our UI's value may suggest a point which is nearer to A than B. Then similarly, in that very order, we'll have to subdivide BC using B as the starting point, not C, so that we can have consistently same order followed. And similarly, having done this, जब हमारे पास दो पॉइंट्स आ जाते हैं तो उन दोनों पॉइंट्स के अंदर भी जो स्टार्टिंग पॉइंट होगा वो पहले लाइन सेगमेंट पे फाइंड होने वाला जो मिड पॉइंट था वो होगा, और दूसरे वाले का मिड पॉइंट जो है दैट वुड बी यूज्ड एज अ सेकंड पॉइंट, और फिर उसको हम फर्दर सब डिवाइड कर रहे होंगे. To define this curve in a coordinate system, let's assume that point A is given as xa, ya, and B is given as xb, yb. Then the coordinates of points D and E for some value of ui can be given as xd equals xa plus ui times xb minus xa. Similarly, yd equals ya plus ui times yb minus ya. Please do note the role of ui over here. So making use of these relations, we'll be able to come up with the values for xd and yd. For the point D, let's mark it as equations 2. And similarly for E, we'll say that xe equals xb plus ui times xc minus xb. And for ye, we say ye is equal to yb plus ui times yc minus yb. Let this be marked as equation number 3. Please note the order in which these coordinates are appearing. We have maintained a consistent order in both the sets of equations 2 and equations 3. The coordinates of point F for the same value of ui, they would be given as xf equals xd plus ui times xe minus xd, and yf would be given by yd plus ui times ye minus yd. You can see that having found points D and E, it would be easy, following the same rule, to find coordinates for point F. So whatever value of ui we might have used to come up with the D and E, the same ui would be used in turn using D and E as well to come up with the coordinates of point F, which would be on the curve in this particular example. Why in this particular example? Because यहाँ पर हमने सिर्फ 3 points लेके हम चले हैं. We can have more control points as well, as we will see shortly. To obtain xf and yf in terms of the coordinates of points A, B and C for any value of ui in the unit interval, we substitute appropriately from equation number 2 and 3 that we've already found, 2 relations in each, into equations of number 4 for the plane curve. After rearranging the terms to simplify, we'll find something like this. The coordinates of the point F, xf and yf would then be given by these 2 equations. xf equals 1 minus ui squared xa plus 2 ui times 1 minus ui times xb plus ui squared xc. That would be xf, and yf would be 1 minus ui whole squared ya plus 2 ui times 1 minus ui yb plus ui squared yc. Thus we have expressed xf and yf in terms of the original points that were given as the control points for our curve A, B and C. We have gotten rid of the intermediate points D and E. We have expressed our required point on the boundary of the curve using the original native control points. We generalize this set of equations for any point on the curve using the following substitutions, saying x of u equals xf and y of u equals yf. And we mark this as equation number 6. Let x0 be equal to xa, x1 be equal to xb, x2 equal to xc. And similarly, let y0 be equal to ya, y1 be equal to yb, and let y2 be equal to yc. So now we have x0, x1, x2, y0, y1, y2 in place of xa, xb, xc, and ya, yb, yc. Let's mark this as equations 7. Now we can rewrite the equation number 5 as x of u equals 1 minus u whole squared x0 plus 2u times 1 minus u times x1 plus u squared x2, and y of u can be given as 1 minus u whole squared y0 plus 2u times 1 minus u times y1 plus u squared y2. Please note that what we have done over here is that eliminating a, b, and c, we have introduced the concept of first, second, and third point. x0, x1, x2 are the x coordinates of the 3 points, y0, y1, y2 are the y coordinates, and we have expressed x of u and y of u in place of the xf and yf that we took example of to start with. Let's mark this as equations 8. This is the set of second degree equations for the coordinates of points on the Bezier curve based on our construction. We express this construction process and equations 8 in terms of vectors with the following substitutions. As we have already talked about, the idea of expressing these equations in terms of matrices and vectors so that our subsequent processing can become efficient. So let the vector p0 represent point A, p1 represent point B, and let p2 represent point C. From the vector geometry, we have D point given as p0 plus u times p1 minus p0, and point E can be given as p1 plus u times p2 minus p1. Now if we let f be p of u, we see that we can write p of u equals p0 plus u times p1 minus p0 plus u times p1 plus u times p2 minus p1 minus p0 plus u times p1 minus p0. Having replaced the values, a, b, and c are now replaced with the p0, p1, and p2 vectors, and we can now have equation in terms of p of u. Let's mark this equation as equation number 9. We rearrange the terms to obtain a more compact vector equation of a second degree Bezier curve as this: p of u equals 1 minus u whole squared p0 plus 2u times 1 minus u times p1 plus u squared p2. We have rearranged the terms of equation 9 and have simplified it to come up with this expression that says p of u now is equal to 1 minus u whole squared times p0 plus 2u times 1 minus u times p1 plus u squared times p2. Let's mark it as equation number 10, where the points p0, p1, and p2 are called the control points, and p is the point on the curve, the one that we are looking for. The ratio u is the parametric variable that takes its value in the range 0 to 1. Later we will see that this equation is an example of the Bernstein polynomial. We will be talking about that later on. For the moment, we are just referring to this for academic purposes only, for completeness. Similar constructions apply to Bezier curves of any degree. In fact, the degree of a Bezier curve is equal to n minus 1, where n is the number of control points. So although we have tried to understand the concept making use of a very simple form where we had only 3 points A, B, and C, but the fact is that we can have these control points as many as we feel like. We can have n points defining a Bezier curve. In that form, of course, there are going to be more requirements of midpointing, finding out points on all those segments that frame the control points or control polygon of the curve. Whenever we have multiple points, if we join all the points together and then finally nth point with the first point, the picture that we get is typically called the control polygon, because this is a polygon that controls the shape of the curve. So here we are talking about control points that are controlling the behavior of the curve or the shape of the curve, but they are not all being interpolated. The curve is being approximated by these control points, and only the first and the last point, the end points of the curve, they are actually interpolated. So curve physically starts at the point number 1 and ends at point number n, but all the points in between first and nth, they are used as control points, only approximating the behavior or shape of the Bezier curve. The next figure shows the construction of point on a cubic Bezier curve, which requires 4 control points, A, B, C, and D, to define it. The curve begins at point A, tangent to the AB, and ends at D and tangent to CD. We construct points E, F, and G such that we can divide them into those segments. AE over AB equals BF over BC, which equals CG over CD, which equals UI. So the basic idea is the same, that we started off with those 3 points, A, B, C पॉइंट थे हमारे पास, तो नेचुरली हमारे पास 2 सेगमेंट्स थे, 2 टेंजेंट्स थे जिनके बारे में हम बात कर रहे थे, एंड पॉइंट्स के ऊपर ही थे दोनों, और उनके ऊपर से हमने जब यूजिंग द गिवन रेशियो UI, जो आर्बिट्ररीली हम चेंज करेंगे फ्रॉम सम मिनिमम वैल्यू टू सम मैक्सिमम वैल्यू, उसको यूज करते हुए हमने 2 पॉइंट्स फाइंड आउट किए थे उन दोनों सेगमेंट से, और फिर उनके दरमियान में अगले स्टेप में एक और पॉइंट फाइंड आउट किया था. अब यहाँ पर हमारे पास नेचुरली क्यूबिक की हम बात कर रहे हैं, दे आर गोइंग टू हैव 3 सेगमेंट्स, और तीनों सेगमेंट्स के साथ वही सलूक करना है हमने यूजिंग द सेम रेशियो UI. अब सेगमेंट AB को आप ब्रेक करेंगे, BC को करेंगे और CD को करेंगे, और तीनों को जब आप इनके ऊपर पॉइंट्स ढूंढेंगे, तलाश करेंगे, तो आपके पास जो डिवीजन बनेगी वो उसी फॉर्मूला के तहत होगी जो कि एप्लीकेबल था हमारे सिंपलेस्ट केस में भी. सो वी आर गोइंग टू हैव AE over AB equal to BF over BC, which is equal to CG over CD. The ratio of these divisions would be the same, equaling UI at any given point in time, because I का मकसद यही है कि हम इस U की वैल्यू को सक्सेसिवली चेंज करते चले जाएंगे to find new points. Let's mark this as equation number 11. What you're looking at is a geometric construction of a cubic Bezier curve on your screens right now. अब आप इसमें देख सकते हैं कि number of steps involved जो हैं before we end up with a point on the curve वो बढ़ गए हैं. The curve is defined by the 4 control points A, B, C and D. So originally हमारे पास जो हमारी control polygon बनेगी वो सिर्फ A, B, C और D पर मुश्तमिल होगी, लेकिन उसके बाद जब हम using some value of UI सेगमेंट बनाना शुरू करेंगे, इनकी मिड पॉइंटिंग करेंगे, तो A, B के दरमियान में हमें पॉइंट E मिला, B, C के दरमियान में पॉइंट F तलाश किया हमने, और C, D के दरमियान में हमें पॉइंट G मिला. अब इन जो नए पॉइंट्स हैं इनको अगर आप सिर्फ देखिए, भूल जाइए A, B, C और D को, तो ये नए पॉइंट्स क्या हैं? E, F और G. Don't they look like the very case that we started off with? 3 points वाला जो A, B, C वाला हमने केस शुरू किया था, वैसी शक्ल नहीं बन गई. Now the control points that we will be playing with in the next iteration, those would be E, F and G only. अब E, F, G के साथ उसी UI के साथ हम वही सलूक करते हैं, फिर मिड पॉइंटिंग करते हैं. E, F के दरमियान में पॉइंट H तलाश किया हमने, और F, G के दरमियान में पॉइंट I तलाश कर लिया. अब इससे अगले स्टेप में H और I को यूज करेंगे हम, और इनके दरमियान में जब हमें पॉइंट यूजिंग द सेम UI जो पॉइंट मिलेगा J, दैट वुड बी आवर लास्ट पॉइंट इन दिस प्रोसेस, एंड दैट वुड बी ऑन द बाउंड्री ऑफ द कर्व. सो ये वो प्रोसेस है जो कि हम बार बार रिपीट करते चले जाएं तो हमें पॉइंट्स ऑन द बाउंड्री ऑफ द कर्व मिलते चले जाएंगे. ऑफ कोर्स वील बी वेरिंग UI इन ईच आइटरेशन. एक सेट ऑफ आइटरेशंस में UI सेम रहेगा, मगर उसके बाद हर सक्सेसिव सेट ऑफ आइट्रेशंस के लिए हम ui की वैल्यू जो है उसको चेंज करते चले जाएंगे. वी स्टार्ट विद से 0. अगर ui को हम 0 रखते हैं इनिशियली तो वील बी टॉकिंग अबाउट द स्टार्टिंग पॉइंट. एक्चुअली हम a की बात कर रहे होंगे, और अगर उसको हम 1 पे ले जाएं तो एक्चुअली हम इस स्पेसिफिक सिनेरियो में पॉइंट d की बात कर रहे होंगे, एंडिंग एंड पॉइंट की. और इसके दरमियान में जितनी वैल्यूज हम उसको देते हैं ui को, दोज वुड हेल्प अस फाइंड पॉइंट्स ऑन द बाउंड्री ऑफ द कर्व. On EF and FG, we locate H and I respectively such that EH over EF, the ratio, equals FI over FG, which equals UI. So, UI वही रहेगा जो इससे पिछले स्टेप में था. Let's mark it as equation number 12. And finally, on HI, we locate point J such that HJ over HI equals UI, and we mark this as equation number 13. We can make no more subdivisions, which means that point J is on the curve. If we continue this process for a sequence of points, then their locus defines the curve, and that's what we would be interested in finding. If points A, B, C and D are represented by the vectors P0, P1, P2 and P3 respectively, then expressing the construction of the intermediate points E, F, G, H and I in terms of these vectors to produce point J or P of U, that would yield an expression like this. Well, of course, it has been complicated, but you can explain the reason why. Last time we were talking about only 3 points to start with, और उनकी जब हमने subdivision की तो we found 2 points, और उनकी subdivision से हमें 1 point मिल गया. So 3 steps में हम वहाँ तक पहुँच गए थे. But here we are talking about starting off with 4 points, और उन 4 points की जब हम सब डिवीजन करते हैं तो तब हमें 3 मिलते हैं, फिर उन 3 की फर्दर सब डिवीजन से हमें 2 points मिलते हैं, फिर उन 2 की सब डिवीजन से एक फाइनल पॉइंट मिलता है which lies on the boundary of the curve. So using the same scenario that we discussed earlier on for 3 points, उसी को हम मैप करते हैं onto 4 points. So this is the expression that we are going to get for P of U. Let's mark this as equation number 14. Now this awkward expression can be simplified pretty nicely to come up with the expression that you are seeing right now. P of U is equal to 1 minus U cube P naught plus 3U times 1 minus U whole squared P1 plus 3U squared times 1 minus U times P2 plus U cube times P naught. This is a resultant of simplification of the last equation number 14. Let's mark this simplified expression as equation number 15. The geometric construction of a Bezier curve shows how the control points influence its shape. The curve begins at the first point and ends at the last point. It is tangent to the lines connecting the first 2 points and the last 2 points. The curve is always contained within the convex hull of the control points. What is convex hull? Actually, when I talked about that control polygon which is made out of the given control points, that actually forms the convex hull. That is a convex polygon that is formed using all those control points. No matter how many times we swivel the points in between, but ultimately the outermost outline of those set of points, the control points, that would be forming a convex polygon, and that convex polygon would actually be defining the convex hull of the Bezier curve. The Bezier curve, by definition, would not fall outside the boundaries of this convex hull or convex polygon, which is typically called the control polygon as well. So this is a property of the Bezier curves, that they do not lie outside the convex hull of the curve. We have talked about the geometric construction. Let's talk about algebraic definition of the same as well. Bezier began with the idea that any point P of U on a curved segment should be given by an equation such as the following. P of U equals sum of Pi Fi of U for I is equal to 0 to n. Let's mark this expression as equation 16, where U is in the range 0 to 1. So u has a value greater than equal to 0 or less than equal to 1, and vectors pi are the control points that we have already talked about. Equation 16 is a compact way to express the sum of several similar terms, because what it says is something like this: P of u equals P naught F naught of u plus P1 F1 of u plus so on up to Pn Fn of u. Let's mark this as equation 17. Depending upon the number of control points, we are going to have these multiple segments of the expression evaluated, of which equation 10 and 15 are specific examples for n is equal to 2 and n is equal to 3 respectively, as we have already seen. N plus 1 functions, that is the fi of u, they must produce a curve that has certain well-defined characteristics. And here are some of the most important ones that we must keep in mind. First, the curve must start on the first control point P0 and must end on the last control point Pn. Mathematically, we say that the functions must interpolate these 2 points. The second is, the curve must be tangent to the line given by P1 minus P0 at P0 and to Pn minus 1 at Pn. So the idea is that the curve must interpolate the starting and the ending point. जो 2 end points हैं, first and nth, उनको ज़रूर interpolate करना चाहिए. और second क्या है कि हमारे पास जो first segment है वो tangent होना चाहिए at the first point, और जो last segment है that should be tangent at the last point or nth point. That's the basic requirement in order to be able to construct or build a Bezier curve. Third, the functions fi of u must be symmetric with respect to u and 1 minus u. This lets us reverse the sequence of control points without changing the shape of the curve as well. So here the idea would be that we should be able to use the same value of u for all subsequent replacements and finding of the subdivisions. And finally, when we come up with one point, that would be on the boundary of the curve, but this process is not necessarily required to be repeated from the first point to the nth, but also we can do the same for nth to the first. And similarly, not only that, we can also do this by having u, its values changing from maximum to minimum rather than from minimum to maximum. That would not matter, and ultimately we will be able to get the points on the boundary of the curve. Some of the characteristics of Bezier curves are listed over here: endpoint interpolation, a fine invariance, convex hull property, linear Peircean, and variation diminishing. Let's briefly talk about each of these. The first one, we have talked about it as well earlier, that the 2 endpoints must be interpolated. So endpoint interpolation is one of the properties. Another one is a fine invariance. A fine invariance से मुराद ये होती है कि अगर फॉर इंस्टेंस हमें कर्व के जो कंट्रोल पॉइंट्स हैं उनको ट्रांसलेट करना हो, we apply translation to the curves and naturally we get a new set of control points. Using those new set of control points अगर हम दोबारा से कंस्ट्रक्ट करें कर्व को, तो कर्व की शक्ल चेंज नहीं होती. That's what a fine invariance means. And then we have the convex hull property that we already talked about, that the whole of the Bezier curve is confined within the boundaries of the convex polygon formed by the set of control points of the Bezier curve. Linear Peircean is another property. Linear Peircean का मतलब ये होता है कि क्या ऐसी कोई सूरत मुमकिन है कि जितने भी पॉइंट्स डिफाइन करें Bezier कर्व को, उन सब को इंटरपोलेट किया जा सके. तो एक स्पेशल केस ऐसा है जिसमें ऐसा मुमकिन है, एंड विच इज व्हेन वी प्रोवाइड ऑल द कंट्रोल पॉइंट्स इन अ स्ट्रेट लाइन. क्योंकि रिक्वायरमेंट है कि एंड पॉइंट्स जो है उन्होंने इंटरपोलेट होना ही होना है. तो जब दोनों एंड पॉइंट्स इंटरपोलेट हो रहे होंगे तो दरमियान में लाई कर रहे होंगे सारे के सारे बाकी के पॉइंट्स. देयरफॉर ईच एंड एवरी पॉइंट in the set of control points would be interpolated. Then variation diminishing. This property means that no matter how many times our convex polygon, the set of control points, swivel, the number of swivels in the curve defined by that control polygon would not be more than those. सो अगर हमारे पास से 0.1 यहाँ है, 0.2 ऊपर है, 0.3 फिर नीचे है, 0.4 ऊपर है, 0.5 फिर नीचे जाके आ रहा है, सो वी आर गोइंग टू हैव काइंड ऑफ अ जिगजैग पैटर्न. अगर हम इन कंट्रोल पॉइंट्स को आपस में जोड़ते हैं तो जो कर्व इनसे डिफाइन होगा उसके अंदर भी वी आर गोइंग टू हैव ओनली एज मेनी वेव्स. द कर्व कैन नॉट स्विवल मोर देन द कंट्रोल पॉलीगॉन. यू आर लुकिंग एट अनदर figure. This is about some different sequences of 4 control points. So Bezier curves that are defined using 4 control points can have different forms, and you're looking at some of those. Look at the C, the last section on the right. Point P0 नीचे है, point P1 is over there on the top, P2 फिर नीचे आ गया और P3 is again above. And you can see what I meant by that variation diminishing. कि हमारे पास जो कंट्रोल पॉलीगॉन है उसके अंदर we are having this n like figure defining that control polygon, और उसी के मुताबिक आपको बेजियर कर्व के अंदर 2 कर्व्स दिखाई दे रहे हैं, the bump and the ditch. There is another problem. The problem is that of local control. इस प्रॉब्लम के बारे में हम डिटेल से तो बात अभी नहीं करेंगे, लेकिन बेसिक आइडिया सिर्फ हम ले लेते हैं. वो ये है कि अगर हम किसी भी बेजियर कर्व को ज़्यादा स्क्यूनेस उसकी बढ़ाना चाहें, जो कर्व है उसको हम ज़्यादा स्क्यूड दिखाना चाहें, तो उसकी क्या सूरत मुमकिन है. बिकॉज जो हमारे कंट्रोल पॉइंट्स हैं वो इंटरपोलेट तो नहीं होते, वो तो अप्रॉक्सीमेट करने के लिए इस्तेमाल हो रहे होते हैं कर्व को. सो व्हाट वी कैन डू, एज यू आर सीइंग इन दिस पिक्चर, व्हाट वी कैन डू इन ऑर्डर टू हैव greater skewness in the curve, that we can repeat certain control points at the same location. For instance, अगर आप नीचे वाली फिगर को देखिए तो we have P0, P1 and P2 primarily. लेकिन अगर हम ऐसा करें कि हम कहें कि जी P0 is the first point और जो second point है वो P1 है और उसी लोकेशन पे एक और पॉइंट P2 भी है और उसी लोकेशन पे एक और पॉइंट P3 भी है और फिर वी हैव पॉइंट P4 एज द लास्ट एंड पॉइंट. तो उस सूरत में आप देखेंगे कि यू कैन इंक्रीज द स्क्यूनेस ऑफ द कर्व डिफाइंड बाय द सेट ऑफ कंट्रोल पॉइंट्स. अ फैमिली ऑफ फंक्शंस कॉल्ड Bernstein polynomials satisfies these requirements, and they are the basis functions of the Bezier curve. Other curves such as the NURBS, they use some different but related basis functions. Basic concept would be related, not the same. Look at this illustration. This is showing Bezier curve basis functions. Precisely, you are looking at 4 of those, which would be joining hands together to form the ultimate form of the Bezier curve. So these functions are termed as the basis functions, and that was what the concept of Bernstein polynomials was. So we rewrite equation number 16 using these basis functions as P of u equals summation of pi bi n of u for I is equal to 0 to n. Mark this as equation number 18. So the basis functions are given as bin of u is equal to ni times u raised to power I times 1 minus u raised to power n minus I, where the initial part of the right hand side, the ni, which means that how many ways we can have out of a population of n items in terms of I. So specifically, if we can have I samples out of the population of n, and that would be described by this expression. Let it be marked as equation number 19. The term ni is the binomial coefficient function from probability theory and statistics, defined as ni is equal to n factorial over I factorial times n minus 1 factorial. You are familiar with the concept of factorial, right? So this ni can be replaced with n factorial over I factorial times n minus 1 factorial. Let it be marked as equation number 20. The symbol sign of exclamation is the factorial operator. For example, 3 factorial is equal to 3 times 2 times 1, 5 factorial is equal to 5 times 4 times 3 times 2 times 1, and so forth. we use the following conventions when evaluating equation 20. If I and u equal to 0, then ui is equal to 1, and 0 factorial is always given as 1. We see that for n plus 1 control points, the basis functions produce an nth degree polynomial. Expanding equation number 18 for a second degree Bezier curve when n is equal to 2 and there are 3 control points produces something like this. Now P of u can be given as P naught B naught comma 2 of u plus P1 B1 2 of u plus P2 times B2 2 of u. This has been rewritten in the form of the Bernstein polynomials. Let it be equation number 21. From equation 20, we find that B naught 2 of u is equal to 1 minus u whole squared, because this is where B naught 2 of u is appearing in this modified version of the equation. From the original equation 20, if you compare, you'll see that this is actually coming in place of 1 minus u whole squared. So let us mark this as equation number 22. And B1 2 of u is equal to 2u times 1 minus u. Let it be marked as equation 23. And similarly, B2 2 of u is coming in place of u squared. So let it be equal to u squared. Mark it as equation number 24. These are the basis functions for a second degree Bezier curve. Substituting them into equation number 21 and rearranging terms, we find that we can write P of u equals 1 minus u squared P naught plus 2u times 1 minus u times P1 plus u squared times P2. Let it be equation number 25. Now this is the same expression as we found from the geometric construction, equation number 10. The variable u is now called the parametric variable. Now let's expand this equation 18 for a cubic Bezier curve where n would be equal to 3. Thus far we were working with n equal to 2. Let's repeat the same process for n is equal to 3 so that we can see what a cubic curve would look like. So that would be given by expression P of u equals P naught B naught 3 of u plus P1 B1 3 of u plus P2 B2 3 of u plus P3 B3 3 of u. Let this be marked as equation number 26. And from equation 20, we find that B naught 3 of u is equal to 1 minus u cube. We're getting back to the same equation that we came up with for the cubic Bezier curve earlier on. So making use of that equation and comparing it with the current one, that's what we come up with, that B naught 3 of u is equal to 1 minus u cube. Mark it as equation number 27. B1 3 of u is equal to 3u times 1 minus u whole squared. And this is also coming from comparing it with equation 20. Let's mark this as equation number 28. B2 comma 3 of u equals 3u squared times 1 minus u, and let it be equation number 29. And finally, B3 comma 3 of u equals u cube. This is also coming from the same equation 20. Keep that in front of you and you'll be able to make sense out of this. Let's mark this expression as the equation number 30. Now substituting these into equation 26 and rearranging the terms produces a resultant like this. P of u equals 1 minus u cube P naught plus 3u times 1 minus u squared P1 plus 3u squared 1 minus u times P2 plus u cube P3. Let's mark this as equation number 31. Bezier curve equations are well suited for expression in matrix form. and we can expand the cubic parametric functions and rewrite equation 31 as this. You can see this on your screen right now. P of u has been expressed as multiplication of two matrices. Of course, the first one is kind of cumbersome looking for the moment, but don't worry about it. The transpose of 1 minus 3u plus 3u squared minus u cube as the first term. The second value in the first column being 3u minus 6u squared plus 3u cube. Third value being 3u squared minus 3u cube. And the final fourth value being u cube. And the second column vector, column matrix being P0, P1, P2, P3. The four control points over here. Mark this as equation number 32. And we can further come up with this expression, dividing that cumbersome looking matrix into a couple of matrices. And that now looks like P of u equals u cube, u square, u1 as a row matrix multiplied with a 4 by 4 matrix having the coefficient values from there. Minus 1, 3, minus 3, 1 being the first row, 3, minus 6, 3, 0 second row, minus 3, 3, 0, 0 third row, and 1 followed by all zeros in the fourth row. The P0, P1, P2, P3 column vector is still there. Let's mark this as equation 33. Now if over here we let u be equal to that row matrix, u cube, u squared, u and 1, and we replace P for the transpose of the row matrix P0, P1, P2, P3, and we place M for that 4 by 4 matrix of numeric values, then we can write equation 33 even more compactly as P of u equals UMP. Given the sequence, you'll be able to make some sense out of it. You know what u is, you know what M is, and you know what P is. So we have expressed P of u in terms of successive multiplication of matrices. Note that the composition of the matrices U, M and P varies according to the number of control points. That is the degree of the Bernstein polynomial basis functions. So that was all about it. Interesting, wasn't it? So we talked about an idea of defining curves using certain points which only serve as control points, which are not all interpolated, but they approximate the shape of the curve. And that's what the essence of the Bezier curves is. And then we were able to express them as Bernstein polynomials, and we were able to come up with matrix representations of the same as well. And the Bezier curve is a very interesting and a very useful idea. Making use of these concepts, we shall be able to come up with multiple applications as well. As I have said earlier as well, that the very finding of this Bezier curves idea also owes to a computer-aided design application as was required at that point in time. And it has its applications in the computer-aided design today as well. So no applications that we can come across would be without the use of Bezier curves. Today we have talked about the basic concept, and we have also extended it to get joined with the idea of Bernstein polynomials, and we have also briefly talked about the basic idea of piecewise polynomials, how complex curves can be subdivided into smaller curves, and each piece or portion of the curve can be defined by a separate polynomial, and those polynomials ultimately together join hands to form the final form of the curve. Of course, there are requirements for that, which you can always get back to your notes and cover them. But the basic idea is that whenever we have pieces of a curve, we have to make sure that the continuity is defined at each junction where those pieces join hands together to form the final one whole. So folks, let's call it a day. We have talked about the curves and specifically Bezier curves today, and we have talked about certain characteristics and variations as well. We will be coming back to you with certain other advanced topics of computer graphics next time, inshallah. तब तक के लिए इजाज़त दीजिएगा। फ़ी अमान अल्लाह।